Okay, good morning. Okay, so let's get started. So this is basically the final chapter. Okay, the final chapter for this module. All right. So as I said in the announcement, there will be one more additional e-lecture that I will put out on the ESP32. All right, but that one is not part of the exam, so it's not examinable, but it is for you to better understand the ESP32 architecture, okay, the dual core system, and how you can maybe, when all the exam is over and you have some time, you can play around with that, all right, and maybe work on some projects. Okay, so I will release an e-lecture, okay, with some demo and so on, how you can maximize the ESP32. All right, so currently we are using it very, very little, correct, mostly as a wireless link, correct, but you can do a lot more with that, okay, which I will try to demonstrate in the e-lecture. Okay, but that is not examinable, okay, that is just for your own self-study, okay, when you are free. Okay, so this will be the last lecture, okay, where it is examinable. All right, so later at the end I'll talk about the exam, the structure, and so on. Okay, yeah, so you have the last lecture today, plus after this will be a tutorial. All right, and project assessment also. Some of you finished it yesterday. We had a good run. I think all the teams did very well. Okay, and Friday we have the remaining teams. All right, so let's get started with the virtual memory and DMA lecture slides. All right, so memory technology, okay, if you look back, if you go and try to look for some historical pictures and so on, you will see some many old different structures of memory. Okay, I'm not sure if you all have been to the computing gallery. Have you all been there? Okay, so if you have been, okay, it's free access every day, I think from 11 to 5. Okay, if you go in, you will see they have a very nice display of the very old memory technology until now. Okay, the very old floppy disk, okay, that we used to have, and how it migrated slowly to a zip disk, and then finally the kind of USB drive that we have. Okay, so there's been a lot of progress in memory and storage over the years. All right, again, these are just some examples for you to look at. All right, so this is the old DRAM chip. So if you have ever used, okay, I'm not sure anybody here still assemble desktop PC on your own. Okay, but if you ever do that or you have done that, you know that, if you go Simlim Tower, then you buy all your parts. All right, then you go back and you fix. So one of the things you'll buy is this DRAM chip. Okay, and then you slot it in to increase the amount of DRAM space that you have. Okay, so these are things that we use to build when you are assembling your own PC. All right, so in terms of memory capacity, the growth is very large. Okay, so every few years the growth is always increasing and increasing. All right, and the bandwidth is also increasing. Bandwidth is how fast I can access my memory. All right, so both of them are increasing, okay, every year, okay, with improvement in technology. All right, but what is the issue? The issue is always that the capacity growth, okay, is always greater than the bandwidth growth. Okay, and the capacity or the ability of your processing power is also much higher than what your DRAM is able to do. Okay, so this is the issue that we have. Okay, so every year, okay, the CPU performance is always going higher and higher. The memory performance is also going higher, but at a slower rate. Okay, so what does this mean? Okay, what does this mean, or what is the issue here? The issue is that your processor can process information very fast, correct? So when I fetch an instruction, I can process or execute the instruction very fast, but then I take a long time to get my data, and I take a long time to update my data, okay, in the memory where everything is stored. All right, so there's always this performance gap, okay, between what the processor is able to do and how fast your memory is able to keep up with the speed of the processor. All right, so these are some technologies. So in the past, all right, we used to have SRAM cells. All right, so an SRAM cell is a far more complex device. You all should know all these devices, right? What is this? This 3-pin device is what? Don't tell me you don't know. Huh? What is it? It's a Transistor, correct? You look at me as if I'm talking in Korean, correct? It's a transistor. It's a transistor. Okay, so you have different type of transistors. So you can see down here, to create one SRAM memory cell, you have 1, 2, 3, 4, 5, 6. 6 different transistors. Okay, so it is a lot more expensive. Okay, expensive not only in the terms of the hardware you need, but the space that it consumes as well. Alright, so in the past we used to use SRAM cells to create your memory, but of course the good part is it's very, very fast. Okay, the access is very, very fast, but the density is very low. Okay, because you need a lot of components to store a single bit. Okay, then along came DRAM. Okay, DRAM was a lot more efficient in terms of the space because you only need a single transistor and a single capacitor. Okay, so with DRAM, okay, cells coming in, we can achieve far more increased capacity, alright, but the access time is now slower. Alright, so this is the trade-off. So from SRAM, we transition all to DRAM because we can store a lot more data, but then the access time is now slower. Alright, and of course in the past we used to have this. This is the traditional rotating hard disk. Okay, I think now it's almost phased out. Correct, everybody is using SSD now. Okay, but it is still SSD or your hard disk. It is still a much more slower device. Alright, but we still need it because you have a lot of storage at a much lower price. Okay, so it is still needed as part of your entire system. Alright, so generally when you look at everything, okay, when you look at everything, what do we want? We want this. Alright, ideally we want a memory that is very, very large, very, very cheap, but at the same time very, very fast in terms of access. Okay, but currently we do not have that. Okay, we don't have that. We have different types of memory with different sort of abilities or capabilities. So we have hard disks that can store a lot of information but it's very slow. We have your register, which is internal to your processor, which is very fast but is very limited. Alright, so what you want to do, we want to be able to put everything together into a complete system. Okay, we want a big and fast memory, alright, at the same time at a low cost. Okay, now how can we go about doing this? We can say that I keep my small memory closer to the CPU and my large memory further away from the CPU. Okay, so this is sort of the hierarchy. Alright, so at the top we have the registers where they are internal to the processor. So anything that's internal to the processor is very fast because I don't need to go out. I don't need to go out to get any information. It's all internal to the processor space. And then you have your SRAM, and then your DRAM, and then your hard disk. Okay, so the whole idea is this, alright? Whatever that I need to use frequently, I keep it closer to me. If I don't need to use it frequently, I keep it further away. Alright? So a simple analogy you can think of is how you use your Dropbox. Okay, so I think all of us got Dropbox, correct? Okay, on our system. And when we install Dropbox, the default setting is what? All the files are online. Correct? So everything is online. But the moment you want to use something, you double click, it will download for you. Correct? So the idea is what? Since I want to use it now, I move it from a further away place, which is offline, to a space that is close to me on my hard disk. Correct? And then I can work on it. Once I'm finished working on it, I can switch the file back to offline. Switch back to online. That means it frees up the space on my hard disk. Correct? Then I move it back to online storage. So it's the same concept. So if I'm going to use something regularly for this time period, I keep it close to me. Once I'm done, I can move it back online. Alright? And why does this work? Okay, it works because of this thing called the principle of locality. Okay, so what is this principle? Okay, so the idea is that if you look at your code, generally, okay, there will always be loops in your code. Okay, so you may run some sequence and then you will repeat some loop again and again before you go on to another section of the code. Alright, so though you have sequential code, but there will also be a lot of chunks where there is some loop, okay, or some section of the code that keeps repeating itself for a while. Alright, and if I have some code or some part of the code that repeats itself for a while, it also means that the data that is associated with that code would also be used again and again. Correct? So if in that loop I'm using variable x, y, and z, then I will use x, y, and z again and again for a while. Alright, and the way I use the stack, also again the same usage of the stack for that period of time. Okay, so we have what we call temporal locality and spatial locality. Temporal means time. Correct? If I use something now, there's a high chance I'll use it again in the near future. Okay, and if I use some memory or some variables currently, I will also use the nearby memory locations quite regularly for that period of time. Okay, so that gives us this idea of what we call a working set. So within a short duration of time, there is a working set that you will use quite regularly while you're executing your code. Alright, and you want to capture this working set and keep it close to the processor so that you don't need to always go out of the processor space to capture this new data. Alright, so what is the visible to the programmer means things that you inherently program in your code. That means the way you write your code, you try to make use of registers or the stack or so on. Alright, so that is things that you do in terms of the usage of the memory. Okay, and when you say it's transparent to the programmer, is things that the OS handles for you or the compiler handles for you. Okay, and this whole solution of virtual memory is managed by the OS for us. Okay, so we don't need to worry about it, but we need to understand how it works. Alright, now similar to virtual memory is another solution called cache. Alright, so both of them have a similar concept. Okay, and the idea is in cache we want to make a small but fast memory closer to the CPU, and virtual memory has a similar concept where you want to use a small amount of memory, which is the DRAM, but we have actual large amount of virtual memory, which is what the process needs in order to execute. So how can I make use of a small memory and map a large virtual memory to a small physical memory? So that is the whole idea of OS, okay, and the usage of virtual memory. Okay, so if you look at this picture, it gives you an idea of how and where we are. So the place where we execute the code is here, correct? The CPU with all its internal registers. Okay, but when I boot up my system, where is everything stored? In my hard disk, correct? When everything is currently powered down, okay, let's say your handphone or your laptop, when everything is powered down, your DRAM is empty, correct? There's nothing there, everything is in a hard disk. So the first time that I boot up, for me to start running things, I need to be able to transfer the processors, the applications, everything from my hard disk to the memory to start executing. Alright? So where do I transfer it to? So there are many layers. Correct? So I will first need to be able to populate my main memory, and then from there I go to my cache, and from the cache I can execute my processor. Okay? Why don't I just directly go to a hard disk and every time fetch from hard disk, then the whole system will become very slow. Okay, because the hard disk is the slowest access in the whole system. Alright, so the idea is I want to have all these in-between layers which give me much more efficient access to the memory. Because if I can access my memory very fast, I can execute my code very fast. Alright, so always remember the bottleneck is the memory. Okay, the processor is very fast. Correct? The bottleneck is the memory, and we want this hierarchy of memory subsystem to speed up our access. Okay? So of course there is this thing called miss penalty, which we will come to in a while. Okay, what if I cannot get what I want, then what must I do? Okay, so this is the idea of virtual memory. Okay, so come back to this process. So what is a process? Okay, so from the discussion in the OS part, we know that when you say a process, is the instance of a running program. So if right now, if I double click on my browser, I launch a process. Okay, and that process is running an instance of the web browser for me. If I double click again, I will launch another instance of the web browser. Correct? But both of these instances are independent of each other. Correct? Whatever I serve on one browser page is not going to affect another browser page. Correct? They have their own memory space, they work independently of each other. Correct? So we already understand this idea because of the context switch, the multi-threading, and so on. Okay, so that part of the OS you understand. Now you want to go a bit deeper to understand how the memory is managed. Okay, so when I launch a process, it requires a certain amount of memory, correct? How does the OS manage this memory requirement for us? Okay, so the whole idea of any process, okay, the memory requirement can be broken down into these 5 main areas, correct? The text, okay, which is the code that we execute. The data, okay, which is the initialized, global, and static variable. Okay, then we have your BSS, which is uninitialized, global, and static. Then we have the heap and then the stack. So these are the 5 basic elements of any memory associated with a process, okay, when the moment you launch. Okay, so what is virtual memory? Okay, so a virtual memory is the total amount of memory space that the program can refer to. Okay, so it can be a very large range of memory because it is a virtual memory. And what you want to do is the process can have all this virtual memory allocated to it. Okay, but we need to map this virtual memory space into a physical memory space that I can actually access the information from. All right. So if I say, for example, I got 64-bit address space, okay, in terms of my process. So every process that I launch, I will occupy some of these addresses. Okay, but my physical memory, okay, again the physical memory is what? The actual physical DRAM that you have. Okay, the physical space that you have. Okay, this virtual memory is a virtualized array of addresses where the program is going to be mapped to in terms of the text, the code, the BSS, the data, and everything. All right. And I have multiple processes because each time I launch a process, I have a virtual memory space associated with that process. Okay, so for example, if I open one Internet Explorer, okay, then one Chrome browser, okay, then one video player. So each of these processes that I launch, to run the application, I have a bunch of memory that I need. Okay, because it is associated with its own stack, its own heap, its own data, its own code, everything. Okay, so I have all of this memory requirement that they're all running concurrently, correct? Because on your system, a lot of these things run concurrently. But in order for all of them to run, I need to make use of the memory space that I have. Correct? So I only have a limited amount of memory space. Okay, your DRAM could be maybe 16 gigabyte, 32 gigabyte, okay? But each of my process requires a lot of memory. All right? So how am I able to squeeze all of these requirements of all the various processes running concurrently onto a small amount of physical main memory? Okay? Then there's also the issue of how to protect it. Okay? If 2 different processes trying to access the same memory, can I protect it? And if I want to share, how to share? All right? So these are some of the things that give you a general overview of virtual memory. All right? And how we solve this is basically to say that instead of a direct association between, okay, the pointer to an actual physical address, I allow myself to point to a reference node, and that reference node can then point to any other location that I like. Okay, this is the idea. Okay? But let's look a bit deeper into how this whole thing works. All right. So what I'm going to do is I'm going to create a way of mapping all my different processes, okay, that I have, process 1, process 2, all the way to process n, onto a single memory. Okay. So let's see how this can be done. So the way we do this is we break up the address space into virtual address space and physical address space. Okay, so the virtual address space is up to 2 to the power of n, this is up to 2 to the power of m. And n is always greater than m. That means my physical address space, okay, is always going to be bigger than my, sorry, this is my virtual address space, it's always going to be bigger than my physical address space. Okay, because your n is greater than m. Okay, so you have more virtual address space and you have lesser physical address space. And now we want to do a mapping. All right. So in a system without virtual memory, what happened? Without virtual memory means the processor will put out the address of where I want to communicate with, which particular register or which particular address I want to communicate with, and that physical address will go out on the address bus, and I will select that address and I will be able to talk to it. Okay, I can extract the data or I can write to the address and so on. Okay, so a simple system without OS, okay, without any virtual memory will behave like this. Now, once the OS comes in, you do not talk to a physical address, you talk to a virtual address. And the virtual address will eventually be translated to the physical address by this MMU, what you call a memory management unit. Okay, and this translates my virtual address to a physical address so that I can talk to the physical address and get what I want. All right? So this is how a virtual mapping looks like. All right? So in the virtual space, okay, in the virtual space you have a lot of different what you call blocks of memory, and each of these memory can be tied to different processors, and the processors could be already cached in the physical memory or it could be uncached. Okay, so if you look at this, for example, this is virtual page 1. Okay, this is virtual page 1 and it is currently cached to physical page 1. Okay, so it doesn't have to be the same number, it could be any number. So it could be a virtual page 2 mapped to a physical page 10. Alright, so we can map to anything as long as we keep track of the mapping. Okay, as long as we keep track of the mapping. Alright, so we just now talk about cached and uncached. What does this mean? So when I say that a page is cached, okay, that means that section of the memory is already copied from the hard disk space to the DRAM. Okay, that means I already have a copy of that information from the hard disk copied over to the DRAM. If it is uncached means it is not yet copied over. It is used but it's not yet copied over. If it's unallocated means I don't need to use this page at all. Okay, I don't need to use this page at all. Alright, so this gives you some idea here. Alright, so if you look at the virtual address space, okay, for example here I can have a very large virtual address space. Okay, and each of these is broken up into blocks. Okay, we call these pages. Each of this is a block which is called a page. Okay, and what we do is we keep copies of these pages from the hard disk in my own physical memory. Okay, so for example, this block is copied to here. Okay, this block is copied to here, and this block is copied to here, and so on. All right. So what does that mean? That means if I'm trying to access this particular memory range, that information is already in my DRAM. Okay? That means I can directly take it and use it. Yeah. Yeah, so the virtual address space is a space that is allocated on the hard disk, whereas the physical address space is the one that's on the DRAM. Okay, so the virtual address space is very big. Alright, because it's the entire range that your address bus can provide. Okay, and the physical address space is what your DRAM can support. Okay, so the idea is we have a lot of space on the hard disk which is virtual, and we want to map it over to the physical. Alright, and how can we do this? Alright, so I know until now a lot of talk, but we never see the example yet. Correct? So when we look at the example, we sort of make sense how this whole thing works. Alright, but the main thing is your virtual addresses are mapping to the hard disk, alright, and to the physical memory if you look at how it works now. Alright, so let's take this example. Take this example. So let's just say I have 16 kilobyte virtual address and 4 kilobyte physical address. Okay, so 16 kilobyte. So this is my virtual address space, and I am mapping it to my 4 kilobyte physical address. Okay, so 16 kilobyte is 14-bit. So how does 16 kilobyte translate to 14-bit? You all should know, correct? Okay, how to convert 16 kilobyte to 14-bit? You just try a calculator, right? 2 power 5, 6, 7, 8, until you hit the number, then you're happy. Alright? So if you forget, you just use your calculator, correct? Okay, so if you anytime forget how to calculate, you just go back to your calculator. And 1 kilobyte is what? 1 kilobyte is to the power of 10, correct? Okay, so 1 kilobyte is to the power of 10, which is 1024. Alright? So 16 kilobyte means is times 16, correct? Okay? So if you want to go back to basics, you start with 1 kilobyte and you multiply by 16 kilobyte, and 16,384, if you go back to your programmer mode, 16,384, you will get hex 4000. Alright, this one is Digital Electronics 101. Okay, so hex 4000. So hex 4000 means what? Okay, so my entire space here is 0x0000 to 4000. Alright, so 4000 means the total space is always 0 to 1 less than 4000, correct? That means the ending address will be 0x 3FFF, correct? Because 4000 in the total space means it's always starting from 0, means the ending is 1 less than that. Correct? So 3FFF means what? Okay, so 3FFF, this will be total of 12 bits. This one will be 0011. So this is 2 bits, correct? So total of 14 bits. Okay, so that's how you get your 14 bit. Okay, so similarly, you have 12 bit over here. Okay, so this is a 14-bit virtual address, and this is a 12-bit physical address. Okay, and now we are saying that we have a page size of 64 bytes. So page size is what? Page is the chunk of information that I copy over from the virtual address to the physical address. Okay, so whenever I copy information over, I copy them in chunks of page size. So it's not just 1 byte, no, it's the whole page must be copied over. So in this case, I have a page size of 64 bytes. So each page is 64 bytes, and it's the same over here. Here also 64 bytes, each page. So I can have multiple pages here. Same thing over here, I have multiple pages. So how many pages do I have? Alright, so since I have 16 kilobyte of virtual address space, and one page is 64 bytes, so 16 kilobyte divided by 64 will be 256. Okay, that means I have a total of 0, 1, 2 all the way to 255 over here. So I have 256 pages on my virtual address space. Alright, and each page is 64 bytes. Same thing on the physical address, it is total of 4 kilobyte divided by 64 is 64 pages. So I have page 0, page 1, page 2 all the way to page 63. Okay, so this is the current design that we have. So we have a virtual address space of 16 kilobyte. Okay, each page is 64 bytes, which gives me 256 pages. Okay, and on the physical side, I have the same thing, 64 byte page size. Okay, and I have 64 pages. So this is the mapping. Okay, this is the current design that I have. Okay, so how many bits do I need, okay, to specify each virtual address to physical address? All right, so the bits that we have, we need to break it up into two parts. One is called the page offset, the other is called the page number. Okay, so what is page offset? Okay, so page offset is for me to access the information within each page. So this 64 bytes, if I zoom in here, I have a total of 64 bytes. Okay, so I have 64 bytes here. Okay, 0, 1, 2 all the way to 63. So once I extract out the whole page, I may not be interested in all the bytes, correct? I may be only interested in some of the bytes within the page. So I must be able to access the bytes that I want within the page. Alright, so I need to know how many bits do I need to specify which particular byte I want. So if it is 64 means how many bits do I need? I need 6 bits, correct? Okay, because 2 to the power of 6 is 64. So I need 6 bits to specify which byte I'm referring to within the page offset itself. Okay, so that is the first thing. So the byte offset is the same for virtual memory and physical memory because the page size is the same. Okay, so that is why over here, this is 6 bits over here. 6 bits and 6 bits over here. Okay, because the page size is the same. So since the page size is 64 bytes, to access any of the bytes that I want, I need 6 bits to specify which particular byte I'm interested in. Alright, so what is left is the remaining bits. So I have total of 14 bits for the virtual address, so this will be 8 bits over here. And I have a total of 12 for the physical, so this will be 6 bits over here. Alright, and it matches up very nicely, correct? Because if I have 8 bits over here, 2 to the power 8 is 256, correct? Okay, and I have 6 bits here means 2 to the power of 6 is 64. So the number of bits that are remaining match up very nicely with the number of pages that I have, because we just saw that I have 256 pages here and I have 64 pages here. Okay, so everything adds up nicely. The lower bits specify which particular byte I'm looking at within the page that I have extracted, and the upper bits tell me which page I'm referring to. Okay, so both of them add up to the number of bits that we set aside for virtual address and physical address. Alright, so where is this information stored? Okay, the mapping between the physical and the virtual. So where is this information stored? It is actually stored in what we call a page table within the memory itself. Okay, so what does the page table contain? It contains a list of all the mapping of the virtual addresses to the physical addresses. Okay, and at the same time it contains an additional bit called a valid bit. So what is the valid bit? It tells me whether the page that I want is still in the hard disk space or is mapped over to the DRAM already. Okay, so let's look at an example here. Okay, so let me skip ahead first to this slide. Okay, when we understand the whole process, then we'll go back to the earlier slide. Okay, so let's say I give you a virtual address now. Okay, I will give you any virtual address. So the first thing that happens is this. This is the first step. The processor gives a virtual address to the MMU. Okay, now after this virtual address is received, I must translate this virtual address to the physical address to get the data that I want. How can I do that? Okay, so the first thing that we do is, because we already designed the system, correct? So just now, if you go back to this design over here, okay, let's say we stick to this design, we know that we split it up into page offset and virtual page number, page offset and physical page number, correct? So we already know that this is the design that we have. Okay, page offset, page number, page offset, page number. Alright, so coming back here, I will split my virtual address to page number and page offset. Okay, the page offset is the same for the virtual and the physical. That means this page offset chunk over here, the number of bits, the 6 bits here, are copied over as the same physical page offset for the physical address. Now what do I do next? The virtual page number is giving me some number, correct? It's giving me a value, and I take that value and map it to an entry in the page table. Okay, so for example, if the value here is 000000001, okay, let's assume the value there is 1, that means I will refer to page table entry 1. If the value there is 5, I will refer to page table entry 5. Okay, so in this page table, so let's say this is entry 0, entry 1, entry 2, entry 3, and so on. So if let's say the virtual page number, the upper 8 bits in this example, has a value of 1, then I will reference the first entry or entry number 1 in the page table. So entry 0, entry 1, and so on. So now I go to entry 1 in the page table. Okay, so when I go to this page table, okay, at this particular entry, in this case entry 1, the first thing that I will check is this bit. Is it valid? Okay, why is this important? Because if the valid bit is set, it tells me that the information that I want, this page that I want, has already been copied over from the hard disk to the DRAM. Okay, if this bit is set, if this bit is 1, it tells me that the page that I'm looking for has already been copied over from the hard disk to the DRAM. Okay, and if it's already copied over to the DRAM, then this bit is set. Then this physical page number holds the page of the DRAM where this page is stored. So this could be any value. Okay, so maybe this value is 000010, something like that. Could be any value, we do not know. But whatever that value is, it will get copied over here. Okay, because the mapping tells me that this virtual page is mapped to this physical page. So once I get the actual physical address, I can go to the DRAM and extract this page. And I get the data that I want. Okay, so that is how the whole translation works. Okay, you start with the virtual address. With the virtual address, you extract out the virtual page number and the page offset. The page number tells me where to look for in the table. From the table, if the value bit is set, I take the physical address number and then put together with the offset and I get the entire address. Okay, and with that I can get the data that I want. Okay, so that is the whole idea. Okay, so of course there is this other option, correct? What if the value bit is 0? Okay, that means the data that I want is not yet copied over. Okay, we will look at that in a while. Okay, so this gives you a nice summary of how the whole thing works. So if I look back at this, okay, so if I have, for example, 256 virtual pages, that means I have 256 page table entry. Okay, so again with this example that we are looking at, since I have 256 virtual pages, I have 256 entries in the page table, and this is how it may look like. Okay, so each entry in the page table will have a valid bit and associated physical page number. Okay, so if the valid bit is set, that means I have a value here. Okay, but if the valid bit is 0, that means it is still in the disk. That means I do not have a copy of the data in my DRAM yet. It is still on the hard disk space. Okay, so that is how the whole thing comes about. Okay, so just now we looked at the example of where the data that we want is already in the DRAM. And that is what we call a hit. Okay, so when you say it's a hit means what? That means whatever that I'm looking for is already copied over. So when I want to get it, it's already there. Okay, so in this example, if my virtual address point to this entry here and the valid bit is set, that means I already have a copy of what I want in my DRAM, so I just directly point to the correct page in the DRAM and extract out this page. Okay, so the data that I want is already there. Okay, so it's good. But what if you have a miss? Okay, that means what you want is not in the physical memory. It's not in the DRAM yet. Okay, so example here, I am pointing to an entry in the page table, but the valid bit is 0, which means that what I want is not yet copied over. Okay, it's not yet copied over. That means it is still in the hard disk space. Okay, so what do I need to do? So this will trigger what we call a page fault. Okay, and when it triggers a page fault, okay, I need to handle the page fault. Alright, so a page fault exception is similar to an interrupt. That means I need to do something at the back end processing. And what does it do? It basically needs to do a few things. First, load the page from disk to physical memory. Okay, that means I need to now copy this page that I want from the hard disk to my DRAM. Okay, so now once I copy it over, I must update my page table, correct? Because before this, my page table said that it was not in the DRAM. But now I'm copying it over. So since I'm copying it over, I need to update my page table to say that it has been copied over. Correct? And now that it has been copied over, I restart my instruction, and when I restart my instruction, the data is already there. Then it will be a success, it will be a hit. Okay, so coming back to this example, if I try to access virtual page 3, okay, so again this is 0, 1, 2, and this is 3. So when I try to access virtual page 3, it triggers a page fault because it is currently still mapped to the disk. So when it triggers a page fault, what I need to do, I need to extract this page and I need to bring it to my physical DRAM. Okay, so when I bring it to my physical DRAM, what are other things I need to factor in? If my physical DRAM, where does it map to? Okay, so if the place that I map to, it is currently occupied, means I need to evict that page and put in a new page. Alright, so in this case, for example, it maps to physical page 3, then I evict that page and then I put in the new page. Once I put in the new page, I will update my page table entry to say that it is valid, and this will be updated here. Okay, that is mapped to physical page 3. Okay, and once this mapping is done, okay, the page table is updated, I will restart my instruction, and when I restart my instruction, I will get what is known as a hit, because the data that I want is already in the DRAM. Okay, so that is what happens with the page hit and page fault. So you can see that this is what we call the miss penalty, just now we saw in the earlier slide. So every time there is a miss, I have to go through this whole process of getting the data that I want and putting it into the table, restart my instruction, then I get a hit. Okay? So of course when you look at this, you say, isn't it very troublesome? Correct? Every time there's a miss, I need to do this. Every time there's a miss, I need to do this. Is it really, are we really better off? Okay? And the answer is yes. Okay, why does it still work? Because of this idea of locality, that when I accessing some data, I will access the data around it quite regularly. If I'm accessing some code, I will access the code around it quite regularly. So this idea of locality still holds true, which is why, even though it may seem very troublesome, it is still more efficient to have the virtual memory than to not have it. Okay, so in terms of managing multiple processes, okay, as we saw just now, I can have multiple processes, process 1, process 2, and so on, and they map to different physical addresses. Okay, and in terms of the protection and sharing, okay, so if I have, for example, two processes trying to access the same process over here, same physical page over here, then I can enable sharing. Okay, I can also make sure that I protect my virtual and physical memory pages by having additional permission bits, okay, within my page table entry. Okay, so just now when we talk about the page table entry, we only talk about two fields. We talk about the physical address, and we also talk about whether the valid bit is set. Okay, but beside the valid bit and the page address, you can also have additional bits to say whether a process that is trying to access this physical page, does it have the right to execute code, does it have the permission to update the memory, and so on. So does it have write access, does it have execute access, and so on. Okay, so there can be additional what we call permission bits that the MMU can help to manage for us to see whether these memory regions are accessible to a particular process or not. Okay, so now let's go back to this idea of address translation, page hit. Okay, so the first step is this, the virtual address comes out, okay, and when the virtual address comes out, I need to map the virtual address to the physical address, which means I need to access the page table. But what is the issue? The page table is also in the memory. Okay, the page table that we are talking about, okay, all this while I'm talking about the page table, but where is the page table? The page table is also in the memory here. Okay, so you can see that I first need to access the memory to get hold of this page table, okay, and go to the correct index, and then from the correct index, if the valid bit is set, then I can extract out the page table entry. So this is step 2 and step 3. Once I extract out the page table entry, then I know the physical page number, then I can have the full address, and then access the address and finally get the data out. Okay, so you can see that even before I can even get the physical address, okay, I already have to first access the memory here. Okay, which again slows down things, correct? Again slows down things. Alright, because if in a situation where I have a page fault, it's even more troublesome. Why? Because the very first time that I put out the virtual address, I try to get the information from the page table here. So the page table is here. And then what do? I realize that the page table entry, the valid bit is 0, correct? Because it's a page fault. So if the valid bit is 0, then what happened? I cannot proceed, correct? I have to raise the exception. Raise the exception means what? Then I need to do a swap, a page swap between the page that is going to go out and the new page that is going to come in. Okay, and after that only, I go back in, update the cache or the memory, restart my instruction, then get the data. Okay, so it's a lot more troublesome, correct? A lot more troublesome when you have a page fault. Alright, because I need to access the DRAM again and again just to get the page table and update the page table. Okay, so to make things a bit faster and more efficient, okay, what have the designers come up with? Okay, to make it even faster, they add what we call a translation look-aside buffer. That means they create a smaller subset of the page table and keep a copy of it inside the processor itself. Okay, so this full page table is in my DRAM, but what I do, I take a smaller subset and keep it within the processor itself. That's what we call an on-chip TLB. Alright, and the idea is, when an address comes in, I try to settle everything that I want within the processor space itself. Okay, and within the processor space itself, once I can get the correct page table entry and it's valid, then I straight away go out and get the address that I want. Okay, so this helps me to minimize access to the physical DRAM. Okay, so you have to always remember, anything within the processor is very fast. But the moment I have to step outside of the processor to access the DRAM or access the hard disk, it becomes very, very slow. Okay, so the idea is I try to keep as much as I can within the chip itself. So the TLB helps to keep a subset of the page table from the DRAM onto the chip itself. Okay, so the behavior will still be the same. Okay, if I have my page table in the DRAM, what would I do? I would take the page number, point to a particular index in the page table entry, and from there I get the entire address, okay, and then access the address. With the TLB is the same thing. The virtual page number will point to an entry in the on-chip TLB, and from the on-chip TLB I take the physical page number, copy it over here, I get the entire address, and then I access the memory. So the behavior is still the same, but it's now far more efficient. Why? Because I don't need to step outside of the processor. Within the processor space itself, I'm able to get this information that I want. Okay? So of course, if the TLB also miss, then you have to go through the whole process, correct? If TLB miss, I go to the page table in the DRAM, and then if the DRAM also miss, then I go to the page swap from the hard disk. All right. So in summary, okay, if you put everything together, okay, the whole process looks like this. So the very first step is this. Okay, the virtual address comes out. All right, and from the virtual address, the first thing that we try to do is we try to look at the on-chip TLB. Okay, if the on-chip TLB gives me a hit, then everybody is happy. All right, what I want is already stored on the chip, then I can straight away get the correct information from the DRAM. But what if the on-chip TLB is a miss? Then I need to go out to the page table in the DRAM. Alright, so this is the TLB miss. Okay, so if the on-chip TLB is a miss, then I go to the external DRAM, update the on-chip TLB. Okay, now after I update the on-chip TLB, then I restart the instruction, I can get a page hit. Okay, but what if the TLB also miss, the page table also is a miss? So I will trigger a page fault. So if I trigger a page fault, what will happen? Then I do the swap. Swap means the hard disk will have to come in and swap out a page from the hard disk back to the DRAM. And then from the DRAM, okay, so that's where the page swap comes in. And then finally I restart the instruction, okay, and then I get a page hit over here. Alright, so of course you may think that why go through all of this trouble? Alright, why don't I just take a 256 gigabyte or 2 terabyte memory and put together with my processor? Then a processor will be like a huge board that you have to carry around everywhere, correct? Okay, so the reason why we have to have all these layers is because everybody wants to do different things with the hardware, correct? Okay, so even if you look at your KL25Z, for example, it is one particular configuration with a certain amount of memory, a certain amount of peripherals, and so on. Alright, then you have a lower end version, you have a higher end version, alright, or different type of processor with, or same type of processor but with different subsystems. Correct? So everybody has a different idea of how they want to use the processor, how much memory they want, and so on. So it is difficult for a manufacturer to come up with a design and just dump a huge amount of memory on it. Okay, it's not a practical solution. So they come up with the processor as a core and all these other ways of designing your system to give you the memory that you want, okay, or the peripherals that you want, okay, and some other free play for you to extend beyond that. Okay, so again, if you put it all together, it is still a far more efficient system than trying to not have it at all. Okay, so the overall performance is still much better, even with all of this hassle that might come along with it. Okay, so that sort of wraps up the whole idea of virtual memory. Okay, so it is still just an introductory concept. Okay, if you really want to learn more of virtual memory or and so on, I think there are other electives you can also take in the future. Okay, that explore more into this area. Okay, now just a few more slides on DMA, just to give you the idea. Alright, so this idea of DMA is something that most microcontrollers have. Your KL25Z also has it. Okay, and the idea is you want to be able to free up your processor, okay, for cases where you want to do a lot of large memory transfer. Okay, so for example, if I give you 2 large chunks of array, let's say this is A and B, and let's say this is 1 gigabyte of data. Okay, and I want to copy 1 gigabyte of data from A to B. Okay, if I ask you to write the code to do it, it's straightforward, correct? You just write a pointer to one address, read from this address and write to this address. Alright, and then you do a loop. Okay, so you can easily do it in a code. Okay, but as we know, if I execute code, I'm making use of the processor. Alright, and this idea of moving memory from point A to point B is a very trivial task, and you rather use your CPU for more important things. Okay, so the idea of DMA is, instead of me having to write code to move data around, why don't I make use of a separate hardware block? So that is where the DMA comes in. All right. So for me to move data around, I need to get access to the address bus and data bus of my system. And what the DMA does is, the DMA has the DMA controller. And what the DMA controller does is, it actually has the ability to take over this address and data bus for us. Okay, so when it takes over the address and data bus for us, it will be able to do this memory transfer, and the CPU is free to do other things. Okay, so it's like a separate hardware block designed specifically just for large amounts of memory transfer between subsystems. Okay, so this gives you the whole sort of sequence, but in summary, basically what happens is, if let's say you do a request, okay, to do a data transfer, then I can transfer that request to the DMA block, and the DMA block can say, you provide all the details, okay, I want to move 1 gigabyte of memory from address A to address B, okay, and then it will go ahead to do everything for me, okay, and once it is done, it can interrupt you and tell you that the whole process is complete. Okay, so again, it could be initiated by the peripheral or the processor itself. Okay, so the OKL255Z has a DMA block, okay, but we didn't have time to go through that. Okay, you can try that, okay, when you're free. Okay, and how does this whole memory transfer happen? There are two main modes of operation. Okay, one is what we call a burst mode. So in a burst mode means the DMA takes control of the entire bus for the duration of the data transfer. So if I say I want to move 1 gigabyte of data between A and B, I will take over the bus, move 1 gigabyte of data, then I will release the bus. Okay. The other operation is what we call the cycle steal mode. That means for every clock cycle, half the time I do this memory transfer, the other half of the time I allow the CPU to take over. So it's sort of interleaved between the CPU and the DMA. Okay. So again, the DMA can be used in either mode of operation. Okay, so that is just a quick overview only on DMA. Again, it is a very useful peripheral, just like your timer or your PWM or your serial interface. It is still a very useful block, okay, when you have situation where you want to move large chunks of data between your peripherals. Okay, so that sort of wraps up the whole chapter and the whole module as a whole. Okay, so like I said, we have come to the end. All right, so let me talk about the important thing. Correct. So of course we have completed. Well done. All right. So we have covered a lot of stuff, and I think the project has been I hope a memorable learning experience. All right. So let's look at the other matters that is important. Okay. So again, TA application I said before. Yeah, so for next acad year, we are rearranging some schedule because for your batch and the previous batch, all 227 was moved to year 3, correct? All right. So we are trying to move it back to a bit earlier. Okay, so next acad year, there's a chance that both the semesters will have a large intake. Okay, we have a large intake because of the students that have enrolled over the last few years. Okay, so there's a high chance we will need a lot of TAs. So look out for the email from the UG office. Okay, so in that email you need to apply, you need to indicate 2271. Okay, then only I can see your name. Okay, so if you email me directly and say you want to apply, I can't do anything. Okay, it only has to happen through that portal. Okay, so you need to apply, then only I can see your name. Okay, so make sure you do that. So any module, whether it's my module or any other module, and you need to do this every semester. So even if right now you're a TA, okay, next semester you still need to reapply again. Your name is not captured and continued on. Every semester you need to apply again if you want to be a TA. All right, so you can apply to all the modules that you're interested in, okay, and then see which module you are able to secure. Okay, so that's the first thing, okay, for those who are interested. Okay, so final exam. So the schedule, when is the date? Do you all know when is the date? Can anybody tell me the date? 2nd May. Okay, So please go and check your schedule yourself. Alright, don't worry, I will post this in an announcement also. Okay, so the schedule, please go and check. Make sure you come to the correct place at the correct time. Okay, so format will be 42 questions. So like I said, I spend 3 to 4 hours in the middle of the night thinking very clearly, very quiet, nice environment, right? Everybody is sleeping, you're the only one awake. Okay, so I spend all that time to think of all the questions and come up with everything. So it's closed book, but the RTX reference sheet will be provided. So you don't need to worry about the OS course and all. I'll provide you with a reference sheet. I'll also upload to Canvas so you have a reference. So it's all MCQ plus true false questions. Similar to your midterm, so you need your OCR form. OCR form will be provided. You need your 2B pencil and eraser. Okay, you can bring along a calculator as well. So all of that I'll put later. So you must return both the question paper and OCR form at the end. Okay, so the coverage will be from chapter 10 onwards. That means from OS onwards. Okay, so all the earlier part on the hardware, the register, setting, all of that is not covered. Okay, so we will not talk about any hardware configuration and so on. It's all only OS onwards up to today's topic, virtual memory. Okay, so if you look through past year papers, sometimes there could be certain topics that you never see before, correct? Then maybe the syllabus change a bit. Okay, so if there is some, like one batch many years ago, I did cache design. One batch I did address decoding and so on. Okay, so sometimes you may see a question which, hey, how come we never covered this before? That means that syllabus is not covered currently. All right, so no need to worry. Okay, so I will send an announcement on this. Okay, just to make sure everybody gets the correct information. But again, it's very similar to your midterm. So MCQ, and we have already gone through the LED states. Correct? The LED states discussion. So that is how the questions will also look like. That means you will have questions with some code where you need to analyze the code, and then from the analysis of the code, you will need to answer based on what is observed. Correct? What color will blink, what color will show, and so on. Okay? So that is important. Okay? So I'm very sure that somebody in our group will not have come for the class, will not have seen the announcement, will not see the video, and will raise their hand and ask me what is LED state. Okay, last year this happened, correct? Okay, so I cannot answer, correct? I already said I will not answer in the exam, so I never answer, and no need to talk about the grade anymore. Okay, so if you don't know what is LED state means, I think you can close shop and go already. Okay, so make sure you know. Okay, I cannot answer all these questions in the exam. I already said clearly. It is your responsibility. I already sent the announcement, I already sent the information, and everything is recorded. So you need to know the example that we went through last week. Okay, so that is your responsibility to make sure you understand that. Okay? Okay, so just some interesting case study that I thought related to OS that you may want to know. So exploration of space and the moon and all is always a nice thing to look at, correct? So this is one case where there was this Mars Pathfinder mission, okay, launched by the US. All right, and interestingly, okay, they were running some OS, and so there's always a communication task, correct? And then there was another science task. Okay, what is the science task? Because usually this kind of rovers on the moon and so on, or Mars, they try to collect some soil samples or some other environmental samples and so on, correct? So all these things are happening concurrently. And then there was some sort of priority inversion problem. Right, a priority inversion problem where a low priority task was hogging the system, preventing a high priority task from running. Okay, and then we have a watchdog timer that triggered, okay, to allow the system back to its normal operating conditions. So what is a watchdog timer? Okay, a watchdog timer is a timer built into your processor that allows your system to reboot if it ever reaches some failure state that cannot be recovered from. Okay, like for example your phone. Sometimes you see your phone, you use, then after a while, it just reboot by itself. Alright, it hang and then it reboot by itself. Okay, why did it reboot by itself? Because the watchdog timer kick in. Okay, it reached a stage where it failed and it cannot recover. Okay, so the timer kick in to reboot to bring it back to a safe state. Okay, so this is a case study. Okay, another interesting one, the Patriot missile bug. Okay, so Operation Desert Shield. Okay, that is what. So it is part of the Patriot missile system. Okay, so you all know what the Patriot missile system, right? That means if there's an incoming missile, you try to blow off that missile in the air. Correct? Or you try to know potentially where it's going to land, so you know whether there's going to be casualty or not. Okay? So the designers of the system actually had a bug, okay, in the software where the clock will drift. Okay, so the internal clock will drift, okay, as you keep the time of the device longer and longer. All right. So what was the fix? The fix is how always we try to fix things. Correct? We just say reboot. Correct? How to reboot? Okay, we just said, okay, whenever after a period of time we reboot means it goes back to square one, then everything is fine. Okay? But the instruction is regularly reboot. Now what is regularly? So this is always a problem, right? Us engineers, the way we interpret things and the way the layman interpret things is very different. Correct? So they never specify clearly, correct, what is regularly. Is it every hour, every 24 hours? No clear information. So the soldiers on the ground just left it on for more than 100 hours. Okay, and then the drift, 0.34 seconds was a difference between life and death, correct? So the calculation said that he's going to land somewhere else, but eventually land on the airfield. All right. So again, these are all important things because as engineers, when we design things, it may not always be perfect, but we must know how to tackle it. All right. So if this is the solution, all right, I mean, if you are going to design the system, what is a better way to do it? Every time the drift exceeds a certain amount, you force the user to reset. All right. Instead of relying on the user to reset, just like how your Windows is, correct? After a while, it will say force to reboot because you must install some security update. It doesn't give you a choice. Right? So the same thing. So if you have some system that is in place where you want to force the user to do something, then you build that into the system. Okay? So instead of giving the user to make an error, all right, and then create more issues later on. Okay, so this is a case study. Okay, so this is the last lecture. I have 2 life hacks for you. Okay, so this first life hack. Okay, be prepared for the opportunity that you seek. Okay, what is this about? So 2 weeks back we have the open house, correct? I think some of you were involved. You all were there for the open house. So of course, during the open house, a lot of parents come, correct, with their kids. And then, so whenever they come to CEG, they always have the same question. What is the question? If my child take a CEG degree program, okay, can he or she take on a pure software job after they graduate? Right? This is always the question I get, correct? All the parents have this. Okay? So what is the answer? Okay? So the answer is definitely yes. And I link back to the last batch that graduated. Okay? So the last batch that graduated, when I attended the ceremony, I was talking to some of the CEG students, right? So one of them, who was also a 2271 TA, he was going to join TikTok as an AI software developer. Pure software job. Correct? Then another student also got a job, also pure software at a bank. Okay, doing back-end software. Okay, database and all this stuff. Alright? So the question is, how come they are CEG student and then they can get this job? Okay, so the truth is this, the employer does not, or no good employer will ever discriminate a CEG student from a CS student. Okay? They will only look at what you say you are capable of doing. Correct? Because every job interview shows a technical test. Correct? So if you lie, the technical test you sure fail one. Correct? Okay? So definitely there is no way that anybody will discriminate your degree for the job that you seek. Alright? So it's up to you to know, okay, that if, I know some of you already decided for the rest of your life you will not touch hardware. And you also decided the rest of your life you will not touch software as well. Okay? And then you do something else, which is also fine. Okay? But if you already have some idea that you want to do something, then you need to work towards that. So work towards that means what? Okay, you can take courses or electives here, or you can also build up your own profile, correct? You can self-study, you can work on projects, you can do stuff that showcase your ability, and then when you go for the technical interview and you can show that you have that knowledge, you'll get hired, no problem. Okay, so there's nobody who will discriminate. Okay, when I was in the industry, okay, as an embedded engineer, all right, there was one guy who applied for embedded firmware job, and he's from a mechanical engineering degree. But his resume, he said, yes, I can do it. So we called him for interview, he passed the technical test, he showed he can do, we hire him. Okay, so he's a mechanical engineering student, but he's doing embedded firmware. Okay, so like I said, it's all a matter of whether you know your stuff and you can show that you know your stuff. Alright, so whether you want to do software, hardware, or anything, as long as you prepare yourself for that, then I think you're good. You're good to take on that role in the future. So this is what I said. So this is the same thing I told the parents as well. Okay, so we have a curriculum, okay, that has hardware and software, but the child is of course free to explore what they want. Alright, and then build up the profile depending on what their interest is. Okay, so that is the first life hack. Okay, so second life hack, go where life takes you. Okay, so for the last few months, interestingly, I don't know why, last few months, I've been receiving a lot of emails from the US. Okay, I think they got hold of my old resume from don't know how many years ago, and they're all asking me to come there and work. Okay, so this is one of the recent emails that I got. Okay, a lot of this email, okay, from US, embedded software lead, don't know what firmware manager, all these things. Okay, so this is really my email sent to me. Okay, so of course I never apply just to let you all know, I never apply. Okay, so they are sending me email. So why am I sharing this with you? Because there is opportunity all over the world. Okay, and why I'm saying that is because this last 1 year, the job market in Singapore is not so good. That's the truth. That's the truth. I was just talking to some students who are going to graduate. One of the girls told me she sent out 100 applications, so far 0 response. 0. That means nobody even called her back yet. Another guy I talked to, he's also 100 plus applicants, only 2 interviews so far. Okay, which is considered very, very bad already. Okay, few years back, before 1-2 months already, everybody get job already before graduation. Okay, but this 1 year has been slow. How will it be 1 year time when you graduate? I do not know. Correct? So I mean the reality is this. Okay, so we do not know how the job market is going to pick up when you all graduate. Okay, if it's good, okay, everybody is happy. Okay, but if it's not so good, then I think if you have an open mind to go abroad, then there's a lot of opportunity. Okay, so I mean, of course, everybody has their own personal responsibilities, family responsibilities, and so on. Okay, but if you keep your options open, I think there are a lot of opportunities everywhere. Okay, for you to explore. Okay, and see where you want to work. Okay, so hopefully the job market picks up here. All right. Okay, then I think by the time you graduate, I think should be good. But if it doesn't, then maybe you can consider elsewhere. Okay, wherever there are opportunities for you to work and grow. Okay, again, like I said, it's a very personal choice. It's not easy to pack up and leave to another country, correct? So you need to think of a lot of things before you decide, okay, to make such a move. Okay, but it's something to consider. But interestingly, if you see, the requirements are things that all of you have, correct? C, C++, RTOS, ARM, x86, multitasking, OS. So all these are things that you have, correct? So you all are capable, all right, of taking on a lot of jobs everywhere. Okay, whether it's hardware or software and so on. Okay, now the last slide, the beginning. So what is the beginning? The beginning is this, correct? So why is it called the beginning? I showed you this picture before, correct? Okay, I showed you this picture before. And why is it the beginning? Because in NUS we don't call it graduation, correct? We call it what? Commencement. Correct? We call it the commencement ceremony. Okay, that means it's the beginning of a new chapter in your life, correct? Okay, so in 1 year's time, all of you, hopefully we can take a new photo like this. Alright, will I still be there? I do not know, correct? Again, like I said, I go where life takes me, correct? Okay, so maybe I'm there, maybe I'm not there. So if you want to know whether I'm still around, you look for next semester 2271. If you see my name there, means I'm still here. Correct? If you don't see my name there, somebody else take over means, then I'm somewhere else. Okay? But anyway, when this thing happens, okay, when you graduate, like I said, it is the beginning of a new chapter in your life, all right, where you navigate, correct? And what you make of it is up to you, correct? And like I said, what you want to do will change over time. Okay, sometimes, right now you have a thought, I want to do this, I want to do this, but after a few years of working, you may change. Correct? A new opportunity might come by. Okay, recently I met one of our graduates also. So when he graduated, he had a scholarship, correct? And he told me that after I finish the scholarship, I want to save a lot of money. I want to open up my own restaurant. Okay, that is his dream. He wants to open up his own restaurant and he wants to run a business. So I say, good for you, correct? So I bumped into him recently, just at a wedding, a friend's wedding. So I asked him, hey, how are things? So he said he finished his scholarship and then now he enrolled as a pilot trainee. So he suddenly had this opportunity. He signed up, he enrolled and he got in, correct? So he just finished all the tests. They have 13 tests, that you have to complete. So he finished all the tests and now he's overseas doing the actual piloting and everything, correct? So if he finishes, he comes back as a SIA pilot, correct? So sometimes your plans will change, correct? You may think that, okay, this is how I want life to be, but maybe after a few years, something else will come. Something else will change and then you say, maybe I try this, maybe I try that. Okay, so again, so as long as you are happy, you know you're doing the right thing, you make the right decisions, okay, then I think you are good to go, correct? Okay, so that's all we have for this module. Whatever I talk about the exam, I will post on the announcement just so everybody is clear. So next week, basically this week we are done with everything. All right, next week we don't have anything. I will release the e-lecture maybe next week or week after next. That is again only for your own self-study. It's not examinable. Okay, just for your own self-study for ESP 32 and so on. Okay, so if I'm still around, okay, next semester 227 will evolve to something even better. Okay, so I just order some stuff in, okay, to make the project even better. All right. If I'm not around, then 227 might become a pure software-oriented module. We do not know. Okay, so let's see what happens. So anyway, still apply for a TA position anyway. Okay, just to support the module. Okay, and then we will see what happens next semester. Can? All good? All happy? Okay, so thank you very much. Okay, and I will see the rest of you all on Friday for the final assessment. Okay, thank you.